Thank you, everyone. Thank you for the nice introduction, and it's a great honor to share some of our recent research on AI safety and trustworthy machine learning here. And it's great to hear the nice talk, and there are a lot of related interactions, overlaps. So I will introduce along the line. Yeah, thank you, everyone. So today I will mainly focus on risk assessment, alignment, and guardrails for generative models. So a little bit background and motivation, right? I think people here all know that indeed machine learning and AI technologies have brought us a lot of nice lives and make our life more convenient and more efficient. However, indeed, these very capable technologies have brought us a lot of security and privacy concerns as well. For example, one of my favorite example back to 2016, which is happened in real world, that the White House Associated Press Twitter account was hacked with phishing emails, spreading the rumor that the White House has been attacked, which again is very easy detected by spam by a normal human being with common sense knowledge, right? But again, the autonomous trading bot will be triggered and dump a lot of stocks within seconds and swap about $106 billion within seconds. And if you say, okay, this is 2016, when we even don't have Gen AI technologies yet. And what happens recently is that last month, I remember, is the Lyft stock price have a huge jump if you look at the history, and it's exactly because there is a small typo, like 500 to 5,000, like one digit typo in the annual report. And again, as a normal human being with common sense knowledge, you will be able to identify, yeah, this must be something wrong. But again, it's picked up by autonomous trading bots, whatever things behind it. And you can see there is a 60 to 70% jump of the Lyft stock price. Even now, this is happening this year, right? And similarly, we know that for foundation models, like large language models, the output could be biased, could be sensitive information, and for multimodality models, like code generation models, code agent, yeah, there are a lot of risks again and again in real world. So that is saying that, yeah, with all this nice and AI technologies, still as a typical say, machine learning or AI developer, we still have a very hard life to build so-called trustworthy and safe machine learning models or systems. And that's also exactly last year, as many of you may know, the White House has published this executive order emphasizing the importance of trustworthy, safe, and secure deployment of AI systems. And similarly with several other regulations like EU Act, GDPR a long time ago about privacy and AI abuse of rights. So with all this, right, I'm pretty sure everyone is aware and alerted about how important AI safety and trustworthiness is, right? But coming back, when we deeply want to contribute to work on something, maybe you still have questions about what is exactly AI safety, right? Some people, when we talk about safety, we have harmfulness, we have privacy, we have fairness, we have all kinds of things, right? How do we talk in a uniform way and also speaking about the same language on the same time? So basically here, in this talk, I will simplify this AI pipeline into this short pipeline here and break it down into 3 pieces, and we go the sum of the representative work into each piece, so that hopefully we can have an overview flavor, but happy to discuss more. So first of all, we can see that we can consider this overall AI pipeline as on the left-hand side, you basically have, say, foundation models or LM agents or whatever types of models, and you can adapt it to different domains like finance, healthcare, autonomous, etc. So the first thing we need to care about and understand from the AI safety perspective is red teaming and risk assessment. So that's the first block I want to emphasize, that yes, we want to generate challenging data in terms of text for foundation model, risk assessment, and for multimodality models, for agents, for code agents, and for all kinds of things. So there are a lot of interesting things in this box, and I will pick up some points from it. And after we understand the vulnerabilities, right, and also understand to what perspective we should follow or what principles we should follow to understand or jailbreak or red team the foundation model enabled capabilities or applications. The second, obviously, is we want to fix it. Fix it have two levels, based on my understanding. One is fundamental fix it, meaning we will fix the model fundamentally, like we change the architecture, we fine-tune it, we do all kinds of things, which is largely open, as in Pudding talk as well. And what if we want a quick fix, right? We can add additional model, which is the guardrail model. For the input and output, you can see both input, output of this whole AI pipeline can go inside to the guardrail model, such that we can serve as a third party to guardrail against some harmful or dangerous or unsecure content. And this way, I wouldn't call it fundamentally fixed, but it's fixed on the application level. So these are the three levels I think will form as an end-to-end life cycle for AI safety and trustworthiness, and therefore we can have this like end-to-end loop and say identify new vulnerabilities and how we can guardrail against it, etc. And next, in this talk, due to the time limitation, I'll mainly go to some part of each component and hopefully get some principles and flavors of it, and then we can discuss more details for some content. So first of all, let's look at the red teaming and risk assessment box and see what's the principles we should follow for red teaming our foundation models, right? We have so many different types of foundation models, and we have so many different perspectives of safety and privacy and security, etc. And how should we follow, right? So mainly the third question here we want to ask is how should we assess the risks of ML models, as we said, and what's the safety and trustworthiness perspectives and principles we should follow and consider, right? So first of all, I want to introduce this decoding trust, which is from principle 1, which is define the safety from use case driven perspectives. And what do I mean by use case driven, right? For example, here the goal is to, as we said, provide a comprehensive trustworthiness evaluation for, say, language models. And here there is an example. I define some of the perspectives. For example, toxicity, stereotype bias, adversarial robustness, like OD, distributional robustness, like privacy, ethics, fairness. So this list can be expanded. For example, additional harmfulness, hallucination, etc. The thing is that based on the use case driven perspective, now we can be on the same page, say, okay, we have this perspective, which one you care the most, and which one you care the most for your applications, so that we can, for each perspective itself, there are a lot of detail. For example, there are additional algorithms, sub-scenarios, blah, blah, blah. I will hide that. And basically on the right-hand side is generated challenging data and prompts, or images, or whatever input the model modality is. So the goal is to evaluate the model from different perspectives so that we can talk about the same language. And by the way, this paper is also the best paper last year at Universe. So that this one itself actually is open source with platform. Everyone can contribute to additional perspectives or just evaluate your own model with the platform. I will discuss a little bit more detail later. So for example, here with this platform, what have we learned from the study, right? So here, this is a high-level overview about closed source and open source models, existing ones, and from the 8 perspectives I just listed out to see what's their high level, the number here is normalized from 0 to 100, so that higher the better, like the more trustworthy, and then we can see different models in the radar plot. So the quick high level takeaway is that, first of all, unfortunately, we can see that no model will dominate others in terms of all these trustworthiness perspectives. Even with the very capable GPT-4, as we know, GPT-4 actually on a lot of benchmarks have achieved #1 on the leaderboard, right? Reasoning, recognition, etc. However, on the 8 trustworthiness perspectives, actually it's not as good as other models, even for many perspectives. For example, for toxicity, right? So this shows that we need to keep in mind that we should understand model safety and trustworthiness, particularly, otherwise their benign performance or capability doesn't represent their safety itself. And the second of all, we can see that there are some trade-offs over different perspectives. Like some models are really good on one perspective, but bad on the others. For example, here, like say llama model, actually the toxicity of it is very bad, but some other perspective is really good. So the toxicity actually is good for that model because it's really conservative, and usually whatever question you ask, they will say, I don't know. I think many of you know that. So that's again a trade-off between utility and the safety itself. So this shows that empirically there are some trade-off among different perspectives. And fundamentally, whether those trade-offs are fundamental, this is a very interesting research question. We have some past work like proof, say privacy and adversarial robustness, like under mild conditions there are bidirectional indication for each other and for some perspectives, but not every other perspective. So I think it's really interesting for us to dig into the foundations of those safety perspectives so that we can understand whether we can aim to achieve the best of all possible worlds, or actually it's an impossible result, right? So that we shouldn't try that hard, and we first know whether it's possible. So I think that is a very interesting thing from this report as well. So next, based on this high-level understanding of different models or different trustworthiness perspectives, I'll give some examples of some perspectives so that we get a little bit of flavor and example of how those models work and what the output look like and what metrics we use and how severe those trustworthiness for very capable model, for example GPT-4 and 3.5, so that we get a little bit detailed understanding about it. So first of all, let's go to the toxicity perspective, because clearly it's a perspective that everyone is worried about. If you have a chatbot, you don't want your chatbot to be toxic, to talk about harmful information, etc. So by the way, all the example in this talk come from GPT-4, just to give a flavor, but you can also find other examples for other models from the paper itself. And here it's two high-level examples. One has normal system prompt, like your help assistant. The other is a jailbreak, like role-playing system prompt, and you can have different types of role-playing or different types of jailbreak system prompt. So you can see here the goal is that we want to generate very stealthy input. For example, if we give the input to Perplexity API, it will not say it's toxic. Basically, it will have low toxic scores. And in the meantime, we want output to be very toxic, such that it will be very stealthy and easy to bypass the guardrail models we have, for example. And then elicits the model to talk toxic content. So this is the evaluation goal, and see how successful that evaluation will be. So here, at the high level, a little bit quantitative result, what you can see here is that we compare, say, very capable model. Like here is a partial example, like GPT 3.5 and 4, with other variations of GPT 3, which assume is not very carefully instruction fine-tuned or RHF. And we can see from the green part, we evaluate, say, GPT 3.5 and 4 compared with other variations of GPT 3 on existing toxic benchmarks. And you can see from the number, it's great that the capable model like GPT 3.5 and 4 have lower toxicity scores, meaning those instruction fine-tuning things are relatively helpful. But if you look at the pink part, which is we give this challenging generative data from ourselves to the model, you can see, unfortunately, the model toxicity level go back to about 100% again, which means that the model are still very vulnerable, and if you give certain instructions or certain very stealthy, challenging data generated in a clever way, for example, we have different ways like energy-based functions, like optimal transport, etc. And it always gets the model to, again, back to very high toxicity level. So the quick takeaway from this example we can see is that, first of all, those instruction fine-tuning RHF structures or algorithms more or less helpful, and you can see on standard benchmarks, it's achieved certain successfulness, which is great. However, they are definitely not the end of the solution, because you can see it's very possible and easy to fool the models and attack the models and make it again vulnerable and output content with high toxicity scores, as you can see here. And finally, we can see that very interesting through actually all the perspectives in this study. that we find GPT-4, for example, is more vulnerable than 3.5, which is at the beginning you feel it's a little bit counterintuitive, right? But then if you think twice, it more or less makes sense because we know that GPT-4 is good and capable at instruction following. Therefore, if your instruction have a little bit like adversarial misleading information, it immediately follows as well, and therefore it becomes more vulnerable. And it's actually true through all the perspectives in this study. So that's again something interesting to know and need to be aware of. And the second, let me go through another interesting perspective called adversarial robustness, which is very related to the adversarial example Patrick mentioned. Here from the text level, that we can see here again, this task is for like a Yelp review dataset, and we want a model to help us give a sentiment, understanding, therefore help us to make decisions. And here, the example, the benign case is that we need to have more experienced cells, which is clearly the negative tone for this sentence. But if we just generate or modify the data with adversarial optimizations, such that the constraint is you want to minimize the small amount of text or like letters, but again, you hope the output could be completely different or aligned with the adversarial target. And what you can see here is that model will automatically change experience to be skewed, which to humans mean the same thing in terms of sentiment, etc. Right? But here, what you can see is that model will immediately be fooled and like output the quality which is the adversarial target. And similarly for other sentences, there are a lot of examples. For example, like who think of like you can change sync to be census, and the model will give you completely different output. And this is through multiple tests. It's not just uncertainty. It's very strong certain like output, adversarial output, I would say. So this again shows a lot of like red flag for us to use the models, because in this way, actually small manipulations and changes will fool the model to be whatever like adversarial target you have. So the quick takeaway from this adversarial study is that, first of all, we can see like the paper models, for example, GPT-4 and 3.5, sometimes demonstrating higher robustness on existing benchmarks as the similar conclusion with the toxicity part we have. But actually, on the other hand, they are still very vulnerable. And again, here, it's very interesting. We can see the adversarial transferability again, which is, you can see here, obviously we don't have white box access to GPT 3.5 and 4, and we'll attack open models like Alpaca, Lacuna, etc., and transfer the generated adversarial sentences or examples to the closed source models, and the access rate is pretty high, like up to 90%. And again, why, following some questions before, like why adversarial example, like transferability exists, and why it's so high, etc. Clearly, I think this is a very interesting direction. And in the past, if you're interested, we have some work for just the deep neural networks and prove the upper and lower bound of adversarial transferability under constrained conditions. For example, how close their benign performance is for the models, and how close the perturbation distribution is. Right? Based on those variables, you can actually derive the upper and lower bound for the adversarial transferability as well. So with this, I hope this gives a quick understanding about this risk perspective itself. And next is privacy. I don't want to go to privacy. I want to go to another principle, which I think everyone is interested. So just quickly go through. So basically, previously we see a DecodingTrust platform for all the text large language models on different perspectives. And we have similar version for multimodality models, like text as output with image input, or with image output, text image as input, right? So basically, follow similar use case-driven safety perspectives. You can define safety, hallucination, fairness, and again, within each one, you have a lot of sub-scenarios. So you have a unified way to define AI safety and do the holistic understanding and red teaming and risk assessment. And similarly, this platform provides red teaming for agents, and also provide actual, I think one of the questions, some malicious code, and see whether the code agent will execute those malicious risky code or something by looking at the outcome. So overall, with this platform, we have open source it. You can play with it, and it's also hosted by Hugging Face as the safety leaderboard. You can go to the leaderboard, and very interesting, we find that people can upload models, their own models for evaluation, right? And we find that a lot of people actually upload the compressed models to evaluate and understand their safety, meaning that many people care about whether their model after compression, whether it's still safe or trustworthy or something, which I think is a very interesting observation and good direction. And there are other platforms which provide automatic red teaming, blue teaming called PalmBench, which integrates with DecodingTrust as well. And by so far, I actually introduced the first principle, which is different use case-driven safety perspectives. And the second, I want to mention another line, or second principle. Don't worry, we only have two principles. The second principle is the regulation-based, of regulation and policy-based, safety, perspectives itself. So basically here, I will quickly introduce. This is a white paper released this week, last week actually. So we passed through different AI regulations, including EU AI Act, executive order, and different things. And we map the safety categories on 4 hierarchies, and the lowest hierarchy contains more than 300 risk categories. So now you can, in a principled way, talk about safety, right? I want to talk about safety following the regulation of EU AI Act. Then you can select the subset and understand it and do a principled evaluation, red teaming, risk assessment, etc., etc. And you can also compare, on the right-hand side, we actually compare, very interesting, the risk perspectives we care about, with the regulation defined in the US, Europe, and China. For Asia regulations, they have a lot of interesting use cases. Somehow their risk coverage is much broader, which is very interesting to observe. And in addition to regulation, there are company policies as well, right? Say here is the OpenAI, Google, all have their own policies about their model safety, their platform safety, different color for the same company, meaning their policy over different time. And we can see how aligned or how disaligned of the safety category we care about, so that we can understand, say, if I have a model, I want to comply with Google policy principle, what I should do. Right now, you can talk about language like this, so that we can be more clear. So basically, these are the 2 principles for the red teaming part I mentioned. Let me see. So the red teaming, we actually mentioned 2 principles in terms of use case-driven safety perspective and regulation-driven. And next, let me use 2 minutes to go through the second component about safety alignment. Apparently, this has a lot of things to do and very open direction. So one small topic I want to touch about is if we align or safeguard the models, etc., how do we provide certifications so that we can, by some way, end the cat and mouse game? So we have certain guarantees, we have certain relief about our model safety, right? Rather than, say, as we showed in the previous slides, we have say, GPT-4, which is well-instruction fine-tuned, etc., etc., and then we show, new attack can attack it, and maybe we patch it, and new attack can attack it again, right? So is there a way that we provide certification verification? That's a hope. But clearly, this is very hard and still very open. I want to point out one word or direction, and maybe many of you have many better directions as well. So one thing I think is very challenging for generative models to define certified or verified safety or robustness is that the output is uncontrollable, right? So previously, for example, for deep neural network, if it's a classifier, we can easily define the certified robustness as, say, lower bound of accuracy. That's all, right? And we can have accuracy certified. But now, with generative models, output is a whole paragraph of text, for example. And how we define the robustness or the certification over that, I think the first challenge is the definition itself. Therefore, here we use a conformal prediction generation risk to define this conformal generation risk. And the goal is to make sure if you give me any model and follow the protocol, generation protocol I have, so that I will be able to give you a lower bound of the generation risk, or upper bound of risk, lower bound of the safety. Or you give me a upper bound of generation risk, say, I want my model to have this much risk at most. Then I can give you protocol parameters such that as long as you follow this protocol, you will guarantee your model will always achieve risk below that. So that's the goal. And here we use, say, we look at the models within LM and the RAG, because obviously we know currently the RAG structure helps us a lot by integrating additional knowledge, right? And the protocol I mentioned is a lambda here. So there are 3 parameters inside the protocol. One is, say, if it's a RAG, how many instances you retrieve. Second is how diverse the generation set is for the tokens. And third is how many tokens you generate. And based on this protocol, I will not go to details, but on the high level, it means that you give you a calibration set, you can calculate your risk function, and here is also the first time you can generalize your risk to arbitrary risk functions. Here is a regal, but you can replace with any risk function. And on the right-hand side, on the top one, you will actually have a controller for this conformal risk. And then on the second part, basically during testing time, you can always use this controller risk controller to conform, to calculate your conformal generation risk and give your generation risk. You can give protocol. I will omit some details. For example, actually based on it, we can prove again RAG is indeed better than LM, which is great, right? Because we all know empirically performance is good, but whether theoretically we can prove that, and indeed it is. So here I want to show some results and see, I think it's very promising for this direction. Because in the past, we know certified robustness and empirical robustness, there is always a big gap. But here with this conformal risk generation, with one example here, the line shows the conformal risk and the dot below it is empirical risk. And we can see very surprising, it's very tight, at least from the evaluation here. And the different, different embedders actually show similar trend, like this certification and the empirical risk are very tight. So this is very helpful, and hopefully this direction on safety verification and certification can move on the way more. Yeah. So let me quickly mention 2 minutes about this formulation. So we finish the whole loop, right? So first of all, we know the risk assessment, so we understand the vulnerabilities. Second of all, how fundamentally we can fix it and give you some verification certification so we have confidence, right? And finally, second is too hard. I think it needs years to go. And how can we quickly fix it now if we want some cheap solutions, right? So here, I want to go very quickly about this. This is another paper at ISMAIL this year, also referred in the LlamaGuard V2 model card, and very interested in their model card webpage. If you're interested, you can search. They say, oh, there's a model more refined than our model. So if you want, you go to look at this paper. So this is the referred model. So basically what do we do, right? A lot of guardrail models can be jailbreaked, as you know, right? Like Llama 3 within 20 minutes, it's jailbreaked, and the LlamaGuard V2 when it's out within 1 hour, I think it's jailbreaked again. So the point is how we can make the guard model not easy to be jailbreaked, right? And therefore safeguard the harmful content information. So the idea on the very high level is that, first of all, data generation is important. Through all my studies, I find data generation is very important. No matter for risk assessment, for improvement, and for guardrail, you definitely need good data. I think everyone knows, but it's a matter of how we generate good data and clean labels, right? So here we use the energy-based function for the data augmentation so that you can controllable generate data under each safety categories, for example. And then there are a bunch of other structures, but the most important thing is, I think, step 4, which we add a cleanest neighbor layer to the transformer models, such that, as we know, for cleanest neighbors, it's actually a very robust model, right? Resilient model against adversarial behavior, jailbreak, etc. But it's not perform well as transformer model, etc. So we compose these two, so you have a structure compose like continuous neighbor and the transformer, such that we don't need to go detail this, and we can see the result is just very effective. So basically, this model achieve much better performance than like a Llama Guard or even OpenAI API under OpenAI moderation dataset. Because as you know, even Llama Guard cannot exist OpenAI moderation API on the dataset because they say, yeah, OpenAI may have the similar data distribution for functioning model, right? But actually, we also don't have the distribution, but just I think because of the data augmentation step, it's actually perform very well. And second of all, it's very interesting here on the second table, every column shows different jailbreak attack, like U means attack, V means attack Vicuna, L means attack Llama Guard, etc. And then transfer the attack to the different APIs. And you can see after all the jailbreak attacks, most of the model can even reduce to 0 resiliency, which is unfortunate. But for this model, surprisingly, it's very resilient. It's almost like 100% all the time. It's very surprising to me at the beginning as well, but welcome to attack it. I think it's very interesting. Yeah. Okay, that's all. Just maybe half a minute. I want to give a little bit of overview about this. I think this is very interesting and motivated me for this whole study. For example, in the very decades ago, we have a map like this, we have a computer like this, and we have a paper called that, right? Not our book, I mean, as asset of humanity, we have this. And later on, after 30 years, we have a map like this with all the internet and everywhere, which is amazing and very fast, right? And I already have a statistic of, say, 2023, how many regions are using ChatGPT. It's already looking like this, right? But then, how about safety and what will safety look like? Draw analogy with the two figures, right? We don't know, and the right-hand figure is just what I prompt GPT-4o to generate a figure projecting how AI safety would develop at that time, right? But yeah, I think that is very interesting and require all the community effort to join together to develop the safe AI itself. Yeah. Okay, thank you everyone.